Ratna, the chairman of the National Science Foundation, to deliver the opening remarks. This is over to you, sir.
Okay, good day, Professor Rajan and the distinguished speakers, dear scientists, ladies and gentlemen. As the chairman of the National Science Foundation, it affords me great pleasure to make opening remarks on this very important and timely webinar titled Grid Integration of Green Power and Energy Storage, organized under the chairmanship of Rajan, the chair of the Steering Committee on Research and Development of Cost Efficiency Energy Sources Storage of the research arm of the National Science Foundation, jointly with the IEEE of the Sri Lankan branch. As the title reads, this is of great topical significance, especially given the energy scenario of Sri Lanka. We still, despite the availability of abundant solar and wind energy, our energy budget over 50% still accounted for by fossil fuel, and Sri Lanka spends over 4 billion annually to import fossil fuels. So that entails not only an economic cost, but also a huge social and environmental cost, and this has been highlighted at the recently held convention in Glasgow. So people have underlined the real necessity to augment the production of green energy. And when you look at the program, I see really top-notch scientists from around the world, especially from Australia, Dr. Brian Pereira, Dr. Tiwanka Vijayakon from Germany, and Dr. Diana Benaika from United Kingdom, and again, Dr. Nilesh Modi from Australia would be joining us. And I understand that this has been really strongly supported by Professor J.B. Ekanaika from University of Peradeniya. We conducted a workshop in the same area in October, I think 27th October, with participation of Professor Ravi Silla, University of Surrey. So there also we had detailed discussion on this very important topic. So this one further consolidates and expands what we have been doing on this very important subject. As we all know, Sri Lanka is endowed with a valuable base of natural resources, including a power, apatite, graphite, and also titanium sand and other minerals that would be useful for production of battery systems. And I hope now this one will go beyond awareness creation to draw up some practical program towards augmenting the production of green energy, so that by 2030, as per our national vision, would be able to reach around 70% of the energy budget through green sources. So I am very happy about this, and I think Professor Ravi, we should be able to form a core team, really inviting the resource persons who are taking part today and also who took part at the last webinar, and also draw upon the expertise available with Professor Ekanaik and others, and high-profile, high-impact team, so that we would be able to take the recommendations emanating from this one and to translate into reality, contribute towards producing green energy in Sri Lanka, and ultimately even making Sri Lanka hub in the production of energy storage systems. I think that is not utopian, but something realistic and feasible given the natural resource base of our country and the intellectual assets already high-profile intellectual assets already lined up in this connection with the National Science Foundation. Again, thanking Professor Ravi, Professor Ekanaik, and our distinguished resource persons for joining this very important webinar in spite of their busy schedule. I wish this event a great success and look forward to some concrete, pragmatic, actionable recommendations emanating from this, so that we would be able to work hand in hand with our experts to make our green energy dream a reality. Thank you very much. I wish this webinar a great success.
Thank you very much, sir. Due to some unavoidable reason, Professor Ravirajan will not be able to join for this webinar. So let's move to the next agenda item. The first presentation will be done by Dr. Brian Pereira. Dr. Brian Pereira is currently working as a principal engineer at the National Connection Teams at Australian Energy Market Operator. He is a chartered professional engineer with over 14 years of experience in the power industry and academia. He has experience in assessing generator connections and advising and supporting network service providers and connection applicants for integrating more than 6 gigabyte of generation to the national electricity market in Australia. This is over to you, sir.
Thank you very much, Madhu. Can you confirm you can hear me okay?
Yeah, Brian, we can.
Sir.
Yeah, thanks for that. All right. Unfortunately, I couldn't get my video on. I believe you cannot see me. Hope that is okay. All right. Good afternoon to you all, and I feel I should say good morning as well. In this presentation, I'm trying to give you an overview of some of the critical requirements that has become essential as part of grid evolving with connection of renewable sources. As outlined, I have picked this topic, so quite a few. Obviously, you might understand the idea is actually not to go into detail, but to touch and highlight the importance of each of these, considering connection of renewables. Some of these are relevant to traditional generator connections as well, but during my presentation, I'll try to emphasize why it is important for renewable connections. Bit of a disclaimer, just to cover liabilities. I believe you all are fast readers, so I'll pause for a moment for you to read, and then I'll start my presentation. Cool. Few notes. I'm so used to some of these abbreviations, so I might use these during the presentation. Try not to, but in case of if I do, you know the meaning of these words. NEM, a National Electricity Market, which is the power system in the east coast of Australia, covering 5 states. NSP, Network Service Provider, similar to Ceylon Electricity Board in Sri Lanka, excluding generation assets. OEM, original equipment manufacturer, like Vestas, SMA, who are very popular these days. There are others as well. BESS, battery energy storage system, generator, anyone who owns and operates the power generation system. To start with, I thought of starting with the grid codes, but as per my experience, so far I believe grid code is the key part of renewable connection as well, like in any other connection too. It sets the technical requirements for a generator connection. The idea is actually when you're connecting a generator, this particular generator can meet this grid code. And the grid codes are typically developed by considering the operating envelope of that power system, which means if a generator can meet this grid code, that means the operator can comfortably operate the system stably and reliably. So grid operators or NSPs develop these grid codes continuously. Sometimes these grid codes are developed to capture an existing gap, and sometimes it is developed to capture any upcoming requirement. In the name, there was a big change to a considerable update to the grid code following 2016 Black event. The expert identified some gaps and also upcoming requirements as well with the addition of these new renewable sources. So if you go back and read, you can find around 2008, there was a significant change of grid code in the name. Similarly, if you might be familiar, current trend, a lot of people start talking about grid forming batteries, another way of controlling the battery storage system. I've seen few players like UK, maybe other countries in the Europe as well, trying to capture the benefit, trying to update their grid codes based on these upcoming technologies. So the idea is actually they get the best out of this system. So in return, it helps the grid operator operate the system more robustly, and also it sets the expectation for people like OEMs who develop the products to meet that grid code. So they will have their products ready. Grid codes are evolving, as I mentioned. It should be, because the technology is changing, operational requirements are changing, and hence it should be kept on updating as well. Thought of giving this example, taking SA Black again, which I mentioned earlier from 2016. In the figure to the left, it shows the part of the power system in the NEM, or National Electricity Market, and specifically this is from South Australia. During the Black event, there were multiple disturbances in the network within a very short period of time, mainly due to a storm. And I have put a reference at the end of the slide. If you get a slide back, you can read the final report. But what happened during that time, actually, SA was rich with a lot of wind farms at the time. And this wind farm had a voltage dip counter, which was set to trip the wind turbines after a certain number of dips. So each of these voltage disturbance increasing that counter, and after some time, these wind farms started tripping. There were a number of wind farms trip. As a result, the generation requirement increased, and the power started flowing through the interconnector, and it exceeded the interconnector limit, and it tripped. So in summary, that was the event. May not be exactly. So when we look back, and the expert identified, okay, this is a requirement that we should cover in our grid codes. To the right, during that update in 2018, multiple full ride-through capability was introduced. Since that came into effect, when the generator is connecting to the National Electricity Market, they have to do an assessment and provide evidence they can meet this particular requirement. That means when there's multiple faults, it's a rare event, but it's critical operationally. Hence, so they do the assessment and show us, okay, this is the capability of this particular generator system, and we have it documented. And then the operators will take necessary precautions considering these. When you get to generator connection, especially in generator system models, become a very critical part, because we cannot simply connect a generator without looking at its impact to the system. So even in traditional generators, it was the case. But we used to use bit simplified models to represent, let's say, if it's a coal power station, it's a hydropower station. We used to use these RMS models, which are somewhat simplified, but it was sufficient at the time to do that studies and understand the impact of this newly connecting generator system. But with the addition of these wind farm, solar farm, and batteries, as you may well aware, these are typically connected via converter systems. I call it inverter. But these converter systems has complex and fast control systems, which cannot be model in these RMS-based tools. Hence, there's a requirement for a different platform. I believe in the past, even OEMs using these EMT models to tune their product, but it's not for kind of studies. But as these battery and based systems are connecting, this has become a requirement. So a lot of network service providers or grid operators use EMT models as part of their assessment to verify or understand the impact of these generator systems before connecting. There are other types as well, but typically these two has become important, especially EMT models has become critical part in the grid connection process. So when you start a grid connection, so we are going to rely on these models quite heavily as we move on. So it's important to understand whether this model is robust. The figure to your left hand of the slide is showing the model testing at the very top of that process, highlighting the importance of it. At the beginning, what we do, we typically, the equipment supplier for this particular project provide a model of the plant. It can be RMS model, as I explained in the previous slide, or it can be EMT model, or sometimes we use both. So as the first step, we have to verify this model is robust enough to do our work, like numerical stability and so on. So that's the first part we do, just to verify that model is good enough to start those assessment. Figure to your right-hand side is model benchmarking, an example of model benchmarking. Model testing and model benchmarking is slightly different. Model testing is, we assess the robustness, but in model benchmarking, we get a confidence on how accurate this model is to represent the particular plant being built. Typically at the beginning, OEMs, or generic equipment manufacturer, provide the models, and they provide sometimes this data as well. It gives the user, let's say, if it can be a consultant working on it, it can be the grid operator, an NSP, network service provider using these models. It gives them the confidence that the model provided is a good representation of the plant they're going to build. So in this example, it's showing test results from a lab and model results, and it has been overlaid. You can see there's some slight difference. You won't get a perfect match, but we apply engineering judgment here and understand it's a reasonable alignment, and we get confidence saying, okay, model is accurate enough, and our study is going to be accurate. Next, we want to cite specific generative models. As per the previous slide, we get whoever developed the project, let's say whoever doing the studies, get the model from the OEM site. It may be not the model for the site. For example, let's say if someone is building a wind farm, it can have many turbines, but the model the OEM is providing can be for one turbine. So the next step is to actually develop a model that represents the site being developed or they're trying to build. We call it a site-specific model. Let's say, for example, there is a new solar farm connecting to this part of the network. And this particular network connection point has specific characteristics like grid impedance and so on. So once they once they put together that general system model that is tuned, the control parameters are tuned as suitable for the characteristics of this particular site, then we call it a site-specific model, which we believe that represents the plant that we build at this particular location. As part of the connection studies, then we move on to prove that using the generator system model that was developed, this particular generator, when that is built, it has the capability of meeting the grid code. These are, most of the time, we use the studies to verify or demonstrate compliance with the grid code, like reactive power support, voltage write-through requirement, for write-through requirement, control, active power control, frequency control, and sometimes protection validation as well. Then the next one, so that's grid compliance. And another part, there could be, you might see there can be overlap between these two bullet points, but I try to keep it separate. The next part of these connection studies are to understand what's the impact of this particular generator might have on the system, existing system. It could be steady state assessment, like, for example, let's say when you are connecting this generator here, there may be situations this line are overloaded under certain operating conditions. So we have to identify those as part of the connection studies. The other assessment we do is power quality. We sometimes use different type of models for those, and stability assessment, like we do with any in project, just to understand transient stability and so on. With connection of renewables, this is a special part. Someone can say it's still stability, but control stability and interactions has become critical. This is where we use mostly those EMT type models that I mentioned earlier. I'm trying to highlight here the criticality of this assessment. In this example, it's a project in the border of New South Wales and Victoria, and it was connecting to the network shown here. So when we did this assessment, we identified there was an existing issue in the system, which was even before connecting this particular project, the system could be unstable, or there could be some control stability issues, existing issues. So through that work, there's a solution developed, and then with that solution, this plant was connected. In Nilesh's presentation, which is the last one in today's presentation, he will cover some of the solutions that are applicable for this kind of situation. So I won't touch that. This is another example why connection studies are important and some use of some particular models are important. As you can see, again, this is the power system in South Australia. North side of it, there are lots of wind farms. You can see those red circles representing wind farms. And this particular wind farm, when you do the connection studies, following a certain contingency, which is a fold. Once it is cleared, we noted oscillations, as you can see in the graph, orange line. You can see sustained oscillations. When the investigation, we carried out an investigation to find out the reason and found out that the controls or voltage control gains were too high, and it resulted in this wind farm fighting each other when controlling voltage. So it was retuned, and you can see the blue trace showing more stable operation. So as I mentioned, with connection studies, we understand how this particular project might have an impact on the existing system. Let's say we are connecting a wind farm to this part of the network, and as a result, the grid operating envelope, the range where we operate the envelope is reduced because of this wind farm connection, and when it is operating at the maximum output level. So this reduces the flexibility for the operator to operate the system, and sometimes it might increase the price of electricity with this constraint as well, so which is not preferable. Then through the studies that I mentioned earlier, we identify these kind of situations and develop constraint and apply those when in operation. So it could mean that this particular wind farm under a particular condition, grid operating condition, might not be allowed to operate 100%. It might be constrained to 50%. It could also mean not only this wind farm, under that condition, we might be constraining a few other generation in the area as well, just to maintain that grid operating envelope. We might not use constraint all the time in every region. There can be regions where they actually request reinforcement of the grid, and which need investment that cost a lot of money to the project. So it can go both ways. It can be either constraints, or it can be grid reinforcement work before we integrate in these models. So next important part I thought of touching is forecasting. If you consider a traditional, let's say, hydro project or a hydro project or a coal-fired power station, or even a battery. If you know the charge level, water level, or the amount of coal that's there, we know the generator can generate. But it's different in a solar wind farm. It has to be the conditions are changing, wind direction changing, speed changing, radiance changing. So a lot of variables. So for the purpose of dispatch, let's say if we don't predict this properly, that means we have to maintain a bigger reserve for any contingency happen with this availability variation. So for near real time, I'm trying to show here, you had to focus on the left side of the graph. There are a few other things, just disregard that. So from the wind farm, we take certain measurements real time, like wind speed, number of turbines available, and so on. And we pass that on to a forecasting tool. AWFS stands for Australian tool. Once it's to the system, it predicts a given time. It's typically in the name, it is 5-minute interval. So it predicts for the next 5 minutes, this is what you're going to produce. Hello, can you hear me? I think I was disconnected. Sorry about that.
Can hear you well. Oh.
Sorry about that. I'll reshare the screen. Can you hear me all okay?
Yeah, Brian.
Yes,
Okay,
Brian.
cool. So in the dispatch, it goes to, I believe you heard up to the forecast that is generated by the tool, and then it sends to the optimal power flow algorithm, which is in this diagram represented as an MD. And it takes all the constraints like I mentioned earlier, price bids, and produce sets the dispatch targets to the other generating system. So this is something done real time. And the next is for the generation planning purposes. So it's important for the operators to know how much generation that comes from renewable so that they can make the generators ready for as required. In this case, we don't have real-time data, but we rely on the system, weather forecast providers, data coming from weather forecast providers, and predict the output for a given time in the future. So that's for the generation planning purposes. So these are two different aspects, but critical in a grid where you have multiple wind farms and solar farm. May not be so critical if there are one or two, but as those numbers increase, these become very critical. Communication system is an important part in battery system, solar and wind. As you see in this diagram, there are a number of turbines. For example, in a wind farm, there can be a number of turbines, but this whole thing is controlled as one system. So it keeps it together by a communication network. I'm trying to show it with these purple lines. It's connected via a communication system. So this communication system carries targets or operation instructions to these turbines, and also carries back its operational data back to the plant controller. So in this communication network is typically connected to switch or other communication devices, and it is feeding into the main controller, which we call plant controller, different names, plant controller, site controller, and so on. So plant controller sends these commands back to the turbine, and it reads data from the turbine so for operational reasons. So let's say if this communication system fails, what can happen? So this is an example from a battery system where the plant was initially designed, assuming scenario, this data transfer is staged or staggered, not at all one time. Unfortunately, the plant was reset. The whole plant was reset at a particular day, and then it starts sending and receiving commands almost at the same time, overloading the communication network. As a result, the plant controller stopped talking to the inverters, charging the battery, and those inverters were tripping. As you see in the middle plot, it is showing that this battery has two feeders. The middle one showing, and it was charging at this time as well. And the middle one showing this each spike showing the disconnection of a part of inverters. The top figure is from the other feeder. And it's trying to compensate for the loss of charging from the other feeder. But overall, it's resulting in this spike, which is not desirable in operation. Commissioning and testing. We designed the system, and someone might say you have done all the studies, but you still want to do commissioning and testing because you designed the system, build it. But each site is unique, and it's normally integrated by using multiple components from different OEMs. So once you build the system, it means that it has never tested anywhere else. And also, model is not the plant. The general system models I mentioned earlier cannot represent every and each behavior of the plant. So commissioning and testing is very important. And it's important to ensure stable and reliable operation and loss of the plant. So what we do typically, we stage by stage, we release the capacity as shown in the figure to the right hand of the slide. While doing that, at each stage, we ensure that grid code compliance, mean there are certain tests that can be done to verify compliance, and then stage by stage release. So the operator get the confidence that this plant will meet the grid code as well. Showing an example for commissioning testing. This particular as to the agreed compact performance requirement, 120 megawatt. It has to generate, absorb 62 megawatts, and showing the plot showing, and it's operating at 120. And through the verification test, they have proved that they can operate at about 62 megawatt absorbing. Another example to show why it is important. This is from a small solar farm in South Australia, operating at its maximum. You can see in the middle plot, it's the flat output, meaning it's operating at the maximum level. But randomly, it's creating this oscillation. When it's investigated together with OEM, they identified it's triggering when the maximum power point tracking was triggering. This is currently being investigated. No one knows the reason yet to why. So we use models, and we tune it, but we don't know whether actually plant is doing what the model is doing. As the next part, the model verification is essential because we are going to use this model heavily on any upcoming studies as well. You see, we overlay model results with site test data that we obtain. I'm showing two examples. One is a perfect match to the left-hand side of the slide, and the other one is a reasonable match. There's some imperfections. We make the engineering judgment, say in the frequency control test, we might go and say, okay, this is not acceptable. You have to improve the model to match the plant. So it can be say, sometimes we say if it's reasonable, we might say, okay, this is okay. This might not have an impact on the studies we do. So that model verification at the completion of testing is an important part as we're going to use those models in any upcoming studies. Lastly, ongoing compliance monitoring is critical because we cannot test everything at the site. And also there are a lot of changes, especially for solar, wind, or battery systems. The OEMs can push firmware upgrades quite regularly because they continuously improve their products. And also sometimes there can be unintentional control setting changes, which mean the plant not might meet the grid code's requirements. And sometimes we cannot test everything during testing. We have to wait for a system event to get this information as well. Just to highlight the importance, this is from a solar farm in Queensland. Maximum capacity was about 56. You can see from the beginning, it's starting up at the beginning of the plot and ramping up generation throughout the day and hitting the maximum around the middle of the plot. You can see it's hitting the map. You can also see these spikes. It's dropping the power to 0, which means at 3 times, which means when the system is operating, the system is losing 50 or 56 megawatt of power all of a sudden without no one knows what that is. And there is some other generator has to compensate for that, which is not ideal. And we investigated that, we identified that it's actually as a reason of the plant controller frozen at these times. And as a solution, they duplicate the plant controller. And when the plant controller was overloaded, it was freezing. And then to avoid that, they duplicate it. So the redundant plant control takes over from the other one when one gets overloaded. Another example to show why it is important to monitor. This is from another solar farm. Its frequency controller was not properly designed or set up. It has a trigger point, but it didn't have a dead band or a hysteresis. As a result, for every movement around the set point, it was making a movement in active power, resulting in oscillations. So this brings to the last of my presentation. I believe what I could deliver what I was trying to highlight, some important things in connecting to consider in renewable energy connections. Thank you.
Thank you very much, sir, for the very informative presentation. And the second presentation will be done by Dr. Tivanka Vichekon. Dr. Tivanka Vichekon is currently the leader of the Power Electronic Technology R&D Group at Huawei Nuremberg Research Center in Germany since 2016. His current research interests include power electronic converter topologies, modulations, control, design of converter system for applications in solar energy. He holds more than 21 granted patents, to date of 25 more patents application pending. This is over to you, sir. The research title is Energy Storage System Integration to Solar PV Challenges, Trends and Application Scenarios.
Thank you very much, Samudhu. Can you hear me well?
Yes, sir. We can hear you.
Can you all see the slides?
Yes, sir.
Proper slide. Thank you. Thank you again for the very nice introduction, and again for inviting for this workshop for NSF and Professor Janaka Nayak and so on. Today, I will try to touch upon some of the aspects on battery energy storage systems, integration to solar photovoltaic systems. So some trends, some challenges and application scenarios. So as Sumudhu mentioned, so my background is power electronics. So I will be talking more on the component sides rather than system sides. So I'll try to give some more flavor into what kind of things we can do in terms of components to support such a renewable energy integration. So currently I'm based in Nuremberg. So I actually Sumudhu went through my experience. So I'm basically a proud product from University of Peradeniya. So Professor Janak also taught me at that time. And I went on to do my PhD on power electronics, and I had the chance to work with very key engineers around Europe and US and so on at General Electric, working on solar photovoltaic and DFIG wind converters and so on. So since 2016, I'm the group leader of power electronic technology, looking into R&D technologies in renewable energy, data center, and UPS applications. So as I mentioned, so my key intention here is to share some of the experience I had with related to power electronics, right? So before going into the topic, I would like to highlight a little bit more on where I work, mainly because so I wanted to emphasize what is happening outside of your world and what companies are actually currently leading this kind of renewable energy activities. So Huawei is well known for ICT infrastructure company. It has a lot of employees. Most of them are R&D. 53% of employees are R&D. And currently, the R&D investment in Huawei is number 3 in the world, and it's the Fortune 500 companies is number 44. And you can see the sales revenue has grown up to 136 billions. So, and this is supported by multiple, of course, segments of the industry. But what is more, I wanted to highlight is more than 10% of the revenue goes to R&D. So this is actually a quite healthy portion. So Huawei's digital power business, where I work, are mainly focused on power electronic activities. What you can see on the green color segments. So you can see the data center where you have the UPS activities, power supply starting from the grid up to the server. So all these power supply chains, that's something that we work on. And also consumer business, we work on adapters, power supplies, and transmitters, and so on. And also the new segment is electric vehicles, so where we work on board chargers, traction drives, and off-board chargers, and so on. And today's discussion is mainly focused on solar photovoltaic and energy storage. That's where so I'll be focusing today. That's the generation side of our business. So as I said, Huawei is investing a lot on R&D. So with especially related to digital power, where the power electronic business is. So you can see there's a lot of activities happening around China, but the largest R&D center is based in Nuremberg. That's where I am actually. So we have 3,000 plus R&D employees around the globe. And we have created so far 1,300 plus patents around digital power business. So with that, I will start the talk on this battery energy storage system integration to solar photovoltaic. Some of the slides I have I'm using today as already say disclosed in IEEE Power Electronic Society event sometime back in early this year. However, I will emphasize a few more related to this energy storage elements at the end for those who have already listened to that talks, right? So I will start with the introduction, and I will go into some terms like levelized cost of energy and what are the trends of PV and also battery energy storage systems. And then I'll try to see why we need battery energy storage systems, some example cases based on Europe and US, and then how we really integrate these battery energy storage systems to photovoltaic. And then what are the components there, and then what are the future trends, and what is happening in the rest of the world, right? So first to the introduction. So you know the sort of photovoltaic systems can be divided into 3 main segments, so based on the scale. So first, the utility scale, that's the largest power plants ranging from several megawatts up to gigawatts. And then commercial rooftops, where we typically connect the photovoltaics into the low voltage grids. And then you have the residential systems. So today discussion will mainly focus on solar photovoltaic in utility scale because of due to the time. So some facts up to now, the total solar capacity in the world, I mean, this is last year figures, already exceeded 700 gigawatts peak. And this has already contributed to more than 90% of greenhouse emission gas reductions. And then you can see the Germany renewable energy share has already gone to 65, planning to go into 65% by 2030. And then beyond it, it will be quite interesting to see how this is going to evolve. And you see on the right side is the worldwide penetration of renewable energies, how the forecast at the moment. So the worldwide 25% is only renewable. This is accounted for all the hydro, solar, wind, and other form of renewables. So you see the portion of solar is expected to be quite high, and second only to wind, right? Just to give some flavor, solar is not just small plants. So what you see in the background is world largest solar plant in the Qinghai province, northwestern province of China. It's actually quite deserted area. It's called Santara utility scale PV project. So that's actually total capacity is 2.2 gigawatts. And this is located in an altitude of 3,000 meters above sea level. And it has 672 PV arrays with 7 million PV modules. So you can see the scale of the power plant. So this is feeding into 330 kilowatt booster stations. So all of these, so like major portion of this power station is run through string inverters. And these are Huawei string inverters. So this all of these PV panels, those are the main investment, can be monitored and diagnosed with very fast diagnosing techniques. And also this power plant can support the weak grid scenarios, short circuit ratios down to 1.2, and is already proven stable in all grid conditions at this moment, and is very well certified already with a TÜV verification on this kind of stuff. So solar photovoltaics is not a small scale, and then it is already reached gigawatt level generation, right? So if you want to see the prospect, so current installed gigawatts, 18 gigawatts based on Huawei's inverters, and then our yearly shipment exceed 30 gigawatts plus. And since 2016, we are the largest supplier of inverters in the world. Right, so let's have a look. What are the types of what are the concepts of solar PV systems available? The main concepts available in the market for utility scale. So one type is called central inverters, where you have multiple strings connected to a DC combiner. And then this DC combiner, the DC cables goes to a central inverter where you convert from DC to AC and then feed into a transformer, and then that goes to the grid. On the other hand, so we have a string inverter concept, where you have a smaller power inverter very close to the several strings, and then multiple of these strings convert into a DC to AC, and then goes AC and combine AC into a transformer and goes on. So what is the difference and similarities these two? Of course, mainly the difference is that in a central kind of inverter, so you rely on a single MPPT for the amount of power you have in the central inverter, which is in megawatts typically. So in case if your plant has some mismatches or your partial shading scenarios, so that you will the whole generation will be dropped, and then you will optimize for the whole plant. So here with regards to string inverters, so the power levels are smaller. So typically a single string inverter has multiple MPPTs. So there you have a chance to optimize each string by string for maximum power point tracking to increase the energy generation, right? So currently, the string inverter has become mainstream in the industry. So into 2020s, 60% of the total inverter shipment is based on string inverter concepts, and then this is expected to increase to 80% next year. So how you optimize this string? So we call it maximum power point tracker. So in solar photovoltaic generation, so you have a PV curve, something similar to this. You have optimum point where we can extract the maximum power out of the solar panel or a string set. So in case of central inverter, so you will optimize at one point where the global optimum is happening, but this may not related to the optimum point of each of the strings. Whereas in the string inverter, where you have multiple optimization, so you see each and every optimum points can be achieved. So this we have accounted, we have estimated typically in a typical plant around 2% increase in the yield. This is similar in the case of mechanical optimizers. So you can also avoid shading in the system when you have mechanical tracking system. So this is also powered by AI and algorithms that we are also actively working on. Right. So solar photovoltaic systems in a utility scale. So as I mentioned, so you are looking at the string voltage levels from 500 volts up to 1,500 volt DC. So the reason we limit to this voltage is mainly because we have the low voltage standard that limits this DC voltage. Going beyond this, we consider medium voltage. And once you go into medium voltage, that all the installation and maintenance require a lot of investment, because you need to train people, you need to have the medium voltage safety. That's expensive. This is one of the reasons that people limit to this voltage range. So the output of a typical inverter goes up to 800 volt AC, again very close to the AC limit, which is 1000 volt AC, and then you feed into the grid as well. So typical inverter efficiency going down to 99% peak, and the euro weighted efficiency. This is what we normally use to benchmark. This includes 5%, 10%, and also 20, 30, 50, and so on. All the power range efficiencies accumulated. So this gives you overall picture how effective your inverter in all scenarios. And then so one of the key points I will highlight later is the maintenance. So this kind of inverters, you don't have active cooling. You typically use passive cooling, mainly because you don't want to you want to avoid maintenance during the lifetime. So typically 25 years lifetime. And then, of course, as I mentioned before, these kind of string inverters can be used to go up to several gigawatts of power conversions, right? And these inverters are typically multi-level. So a typical structure inside is down here. So you have EMI filters on both sides. So you have maximum power point trackers, which are DC-DC converters, and then the main part is the inverter, and then filter, and then you have a chance to disengage by relays as well. So this typically this DC-AC inverters are multi-level. So typical structures of 3-level inverters you can see here. So all sort of a spectrum of topologies. This is a single phase circuit diagram, let's say. So why we use multi-levels? Mainly to optimize efficiency and also to reduce the harmonics generated on the AC side. So So we use the PWM to synthesize the sinusoidal waveform, as you can see. So each of these topologies has their own advantages and disadvantages. One of the key aspects we are looking at is which advantage we could use to reduce the levelized cost of energy in such a scenario, right? So back to the topic again on the levelized cost of energy. So what it means, so in a very, very simplified way, this is the total life cycle cost divided by total life energy production. So in terms of total life cycle cost, you have the capex, you have the opex, and then at the end of the lifetime, if you have any residuals, the disk will be reduced. And then during the lifetime, so how much energy you can accumulate. This is typically either the euro per kilowatt hour or dollar per kilowatt hour is the measurement. So as power electronic engineers, we try always to reduce the capex as well as operating cost. And then you try to increase the efficiency, and then you try to increase your effectiveness of your maximum power point trackers to increase the power generation, right? So let's have a look how the levelized cost of energy is compared with the rest of the energy generation techniques in the world. So you can see on this side, so you have solar photovoltaics with and wind converters, gas combined, geothermal, coal, solar thermal, nuclear, and gas peakers. So this is the historic data, and then you can see the mean levelized cost of energy. So in this case, for megawatt hour, dollars per megawatt hour. And then you can see within the last 10, 11 years that the solar has gone down actually quite a lot. So this is mainly down to reduction in panel prices, reduction in inverter prices, as well as increase in the efficiencies as well. So so you can see it's already very, very close to wind energy prices. So so again, when you see some of the data published recently by NREL photovoltaic systems and energy storage. So for example, in the utility scale, so this is the capex part. You see, so how much is the capex is contributed by each of the components. So you see the inverter was quite small at the beginning, and the major part is the module, the PV module. So you can see recently the PV module price has quite dropped quite a lot. And however, the inverter price reduction is not so considerable. So the cost of you can see the 80% of cost reduction within the last 10 odd years for utility scale and also commercial and residential as well. This is, as I mentioned, mainly led by the component or hardware, especially module and inverter cost reductions. So reducing costs for photovoltaic system, what are the opportunities because of this? So these are the data coming from Germany. So basically Fraunhofer Institute has investigated on the amount of installed capacity versus average price for PV modules. So you can see the photovoltaic panel price has reduced almost 96% since 2000. Yeah, 2000. So this is actually quite attractive for PV business. So you see, so this is another example to show that how the balance of system, including inverter and the rest of the modules, how the proportion. So you see initially 70% of the BOS is related to modules, and then rest is the rest of the components. But you see now because the module price gone down, the inverter and the rest of the part is a considerable portion. So people try to utilize this opportunity, and especially by means of increasing DC to AC ratio. So what does it mean? Basically, so DC means that the amount of PV panels you put it in the DC side, which is DC generation side, and the AC means how much power you feed into the AC grid. So if you have more panels than you can feed into the grid, then DC AC ratio goes high, and usually this is higher than 1. So what happens is that if you have this higher DC to AC ratio, so you at some certain points you have to clamp because of the limitation of your inverter. So however, you still can get more generation compared to a lower DC-AC ratio. So this could be advantageous if the panels prices are low. On the other hand, so there's another opportunity, so that if you integrate energy storage element into the system, so all this energy that you are clipping, you have a chance to charge a battery, and then you can either feed in back to the grid when you have no energy produced by the PV, or you can do self-consumption. So this is actually quite attractive. So basically this PV module costs continue to reduce, which actually favors the higher DC-AC ratio, which couples with energy storage. Right. So why solar PV needs battery energy storage systems? So this is actually some of the issues that we see around the world with regards to increasing renewable energy penetration. So what happens is that if you see the left-hand figure, so the vertical axis is the inverter terminal short circuit ratio that indicates how good your grid. So if the short circuit ratio is very good, actually it's a quite good grid, and going down is actually getting a weaker grid. So here the penetration rate of renewables. So you can see that so currently certain countries have quite good short circuit ratios, but then China and Japan and India, we are looking at a very short circuit ratios not so favorable, but still workable so far. But we are expecting those numbers to go down, the short circuit ratios into 2030, 2025 timeframes. So this is an issue. So this is where we think energy storage can support a lot to tackle these issues, which I will touch upon later. So another issues that we have seen is actually thermal power plants cannot at certain points cannot meet the frequency regulation demands. So you see this plot in daytime during the solar generation. So you have purposely reduce your thermal plant capacity, and then inevitably this thermal power plant capacity is not enough to handle the frequency regulation anymore, so that gives you more trouble. And also our previous speaker explained quite nicely on the grid connection standards and also grid codes and so on. So there are more strict and stricter grid standards are coming in Europe and rest of the world. So this is actually forcing all the renewables to have some form of energy storage to support these weak grids. So apart from that requirement, so of course, if you see the opportunities, so we have more scenarios we can think of. So you can actually, if you have an energy storage system coupled to photovoltaic, you can make the the solar photovoltaic more and more dispatchable. So this also can provide ancillary services to stable the grid, time shifting, and all sort of possible scenarios that you can think of. I will not go through this in detail given the time. Some of the examples you see in certain part of the world that two of our speakers will talk very extensively, hopefully, about this kind of requirements they put through in South Australia. So certain scenarios you have to support the fast frequency response, which requires certain amount of built-in energy storage in your system, right? So solar photovoltaic and storage, is it economical? So we know that energy storage is quite expensive. So, but if you put them together, is it economical? So typically we use a term called LCOSS, means the levelized cost of energy plus solar and storage. So you can see some of the recent data coming from US again. So you see, so here in the blue color is that the US government supports investment tax credits for the investors to include solar and energy storage systems. And the other, the yellow one is without this kind of tax credit. So you see a big difference. So if the government supports actually those energy storage plus solar is actually in par with standalone PV in terms of levelized cost of energy. So this is actually basically if you really want to if the government wants to really take a lead on this, they have to invest, and then they have to provide this kind of tax credits for the investors to come in and then put up this kind of energy storage systems in the grid to support our target for increased renewable energy resources, right? So another example case on the bottom. So I want to highlight this is very specific to Germany because Germany has the highest gross domestic electric prices in Europe and the rest of the world, I believe. So here you see the cost and the price of the electricity per unit, and then this axis is the time. So you see the gross domestic electric price has increased currently around 31, 32 cents per unit in Germany. Whereas if you have a photovoltaic system built in your rooftops, so basically this is what you get out of selling this PV to the grid. So there's a big gap, you know. So if you generate and sell it to the grid, you are selling at quite low rate, below 10 cents, whereas your consumption, so you're paying like 30 plus cents. So this actually one of the key reasons that Germany and the rest of the Europe, so people are more encouraged to basically have their own energy storage systems in their PV, and then do the self-consumption. So here you have some details. You don't get the complete difference between this. You have some losses in between. However, the portion is still around 96% of this difference saving. So self-consumption in small-scale photovoltaic is also very attractive in Germany with storage. Yes. So how battery energy storage systems are coupled to photovoltaic systems? So I will talk shortly. So this is two main aspects. So let's say we have AC coupling and DC coupling. What you have on the left is a DC coupling, and this is AC coupling. So in terms of AC coupling, so you have your photovoltaic generation that translated to DC-DC converter for maximum power point tracking, and then inverter feed into the grid. So it could be that these two could be combined. And then your battery energy storage system is basically coupled through another AC to DC converter through a transformer and then the grid. Whereas in the DC couple system, so after the DC-DC converter, so you will couple through another DC to DC converter, and then you reuse the inverter for both energy feeding to the grid, energy generated from photovoltaic, as well as energy generated from when the PV is not there. If you want to feed in the battery power to the grid, you reuse your inverter. So that needs certain component requirements, for example, bidirectional power flow and battery converters. So this is actually make some differences, but both these solutions could be competitive depending on the case. So you have to analyze case by case which option suits you the most in your scenario. Right. So just to go a little bit more into battery side, so how the utility scale battery container look like. So you see this kind of containers include let's say battery racks. So the battery racks consisting of a pack and then down to cells. So you can see the numbers here, so I would not go through in detail. So you hopefully at the end of this workshop we can share the slides, and then you have a flavor of how some examples of how we build that. So you have this kind of battery clusters. So if you look from the top, so it looks like here. So you have a 6 kind of clusters inside, and each cluster has 21 this kind of battery packs. And the most important thing is to make sure that their lifetime is maintained by proper maintaining the health. So you need to have very good health monitoring. So environmental conditions, you need to have air conditioning and all sort of requirements so that you can keep this high investment portion of your the plant for a lifetime of 15 years. Apart from that, so we also need to do a battery management system. So that battery management system means that each pack and each cell needs to be managed properly. So if they have a mismatch in their charging, and then this mismatch or state of charge differences can cause insufficient battery utilization, and also you will also at the end can lose a lifetime. Therefore, so what you do is actually you have each and every pack level and also cell level, you need to have some optimization. So these are typically power electronic converters, small DC-DC converters, where you operate to maintain their state of the charge at quite close levels, and make sure that when to avoid any damage and cutoff if some packs are not working, and also whenever you want you can shut down to avoid any electrical shocks and so on. So this usually we do on a pack level as well as rack levels, and this will improve the utilization. This will provide the guarantee for our investment as well. So the last part of my talk, so I wanted to touch upon some of the aspects, the key aspects of battery energy storage systems. So why we really need battery energy storage systems for power converters. So coming from a power converter side, actually, so the typical generation is based on let's say a synchronous generator. We know very well. So they are bulk equipment. So if you take a very simple calculation about how a synchronous generator how much so how much energy you have in the synchronous generator versus how much energy you have in a typical converter. So this is not a apple to apple comparison, but just to give you some flavor. So a typical 1 megawatt converter may be operating at 1100 volts, and then you have some capacitors, electrolytic capacitors. This accounts for something around 525 joules. So if you calculate similar on a mechanical energy that you will have in a synchronous generator for a similar power range, you are talking about one magnitude or order of magnitude high. I mean, one can say, okay, a generator is bulkier than a converter, but this is what's where we have the key pain point, right? So if you expect to have similar behavior on a converter-based generation to a traditional synchronous generator, that you are mistaken. So you have a much lower capacity in terms of energy storage to support the grid needs. So this is one of the example case to say, okay, energy storage is a must. So how you do it? Frequency services. So you can if you have energy storage coupled to your to a PV generation, so you have a you can form something called the hidden inertia emulation. So this is what we frequently work with our inverter control to emulate a certain amount of inertia based on this energy storage capabilities. So I would say the battery storage is the piece that needs the PV inverter to provide the power energy needs for frequency regulation. So this basically, you have to have such a capability built in your system. Otherwise, you cannot effectively provide this kind of supports to the grid. So, however, there are some challenges I would not like to go through in detail given the time. So, so of course, you need to have a very good grid frequency detection, rate of change of frequency detection, and so on. But this is actually our key focus in even in our research center, how we improve and continue to improve in our products this inertia emulation. Right? Another few trends I want to highlight. This is my last slide. So let's say, so of course, I explained about solar photovoltaic systems in the residential. I did not go through detail in the residential, but then and the utility scales. But some of the key aspect in the solar PV and EV charging is actually emerging in Europe and also in China. So they are using energy generated in solar and coupled with the battery energy storage system to support the DC microgrids. And another aspect is what we call the virtual power plant. So the virtual power plant is actually is a cloud-based distributed power plant that aggregates the capacities of several heterogeneous distributed energy generation, such as PV, and it could be wind converters and so on. And those, the main purpose of enhancing power generation as well as trading this small scale generation on an electricity market, right? So this is interconnection of charging networks, grids, and internal IOVs, and also vehicle to grid is another aspect that we in discussion. For example, the battery in the electric vehicle could be supporting this kind of activity to the virtual power plant initiation and utilization. So this is what is happening in Europe and rest of the world to support this smaller scale PV plants as well as energy storage systems. So with that, I would summary and conclusion my talk. So string inverters becoming main sort of photovoltaic generation in the world. Actually, cost of PV, solar PV continue to decline due to the panel price drops, and it favors a lot to include the storage, and storage is an essential part of to support the weaker grids and especially high renewable integration to the grid. And storage also opens up a lot of opportunities also to provide solar photovoltaic and also to form grid forming functionalities, and rather than a grid following what is happening at the moment. So of course, with government incentives and other forms of support, I think solar photovoltaic and battery storage systems can become economical for investors, and also who has a standalone PV plants and so on. And then I think in certain part of the world, the self-consumption becomes quite attractive, and therefore so PV with battery storage is very attractive, especially in Germany. Of course, as part of the major investment of battery energy storage system, BMS is very important. And there are some certain paradigm shifts that gives you new application scenarios for this kind of PV and battery energy storage systems. One of the few of them I explained earlier, virtual power plants, and also this participation in the frequency regulation markets and so on. So in essence, an economical and dispatchable energy, renewable energy source that solar PV can become is a must to have a battery energy storage system. Okay, thank you very much.
Thank you very much for the valuable presentation, sir. The third presentation will be done by Dr. Gayan Abenayaka. Dr. Gayan Abenayaka currently working as a power system manager in Ørsted Power in UK. Ørsted is currently the largest offshore wind farm developer in the world. His main interests include power electronic applications in MVDC systems, power systems, and power electronics reliability with the integration of renewable energy and power system planning. This is over to you, sir.
Thank you, Sumudhu. Can you all see my screen now?
Yes, sir.
All right. Okay. Hi, everyone. Good evening, good afternoon, and good morning, everyone. Thank you for the kind introduction, Sumudhu, and hope you all are enjoying the workshop so far. First, I would like to thank Professor Ekanaik and the organizing committee for having me today. So in this presentation, I'm going to touch upon the long distance connection of offshore wind farms and hubs, and basically to provide a high level overview of offshore hubs, wind farm hubs, and energy island concept, which are still at the conceptual and pre-planning stages. And this is the content of the presentation. First, I'll provide an overview of the offshore wind farms and the existing technologies used, and then we'll discuss about the generic challenges. I think in the previous two presentations, this has been broadly addressed. Just to summarize some of the generic challenges in the offshore wind, in the context of offshore wind and the future trends. And next, we'll talk about the offshore wind energy interconnectors and the Danish energy island, which is now in the discussion. And generally, offshore wind technology provides added benefits over its onshore counterpart, such as high energy yield and also less public disturbance for the offshore projects. And there are some of the general statistics I have taken from the recently published Global Wind Energy Report 2021. According to the report, the International Energy Association calls offshore wind to grow as a share of total wind development from 7% in 2020 to 20% from 2021 onwards, which is big rise in the offshore wind development around the world. And its roadmap requires offshore wind annual installation to grow by 7-fold to in 2030 to 13-fold by 2050 to achieve the net zero emission and maintain the 1.5 Celsius degree reduction, the global temperature rise pathway. And it has forecasted that 2,000 gigawatt of offshore wind is required to build to achieve these targets, and where these all these offshore wind farms will be developed. So right now, we only have about 35 gigawatts installed capacity around the world today, primarily in Europe and China. And the offshore wind promises, it comprises currently less than 0.5% of the global installed electricity capacity. However, we could see that this forecast in Asia is emerging. As you can see, like by 2050, about 40% of the offshore wind farm will be developed in the Asia, followed by the Europe. It's about 30%, and also there are Northern American also initiated starting like a lot of projects in their shores currently. And next I'll provide an overlook of the offshore wind turbines and currently what are the sizes and the trends in the offshore wind turbines in the market. To capture the large amount of wind energy at the offshore sites, the size and capacity of a single unit is increasing over the years. Recently, there have been a few announcements of large-scale offshore wind turbines, such as GE Haliade 40 megawatt wind turbine. You can see that the size of the wind turbine compared to a general human being, the ratio. And the Siemens Gamesa has also announced their 14 megawatt wind turbine, and Vestas has recently announced their 15 megawatt offshore wind turbine. And in August, the Chinese manufacturer called Mingyang has announced their 16 megawatt single wind turbine unit, and currently this is the largest offshore wind turbine available in the market. And we could see that there is a trend towards developing larger single unit size wind turbines present. And this is one example I captured from one technical brochure of GE Haliade 13 megawatt wind turbine, which will be installed at the Dogger Bank offshore wind farm towards the North Sea, which will ultimately connect to the UK power grid. And the total capacity is about 3.6 gigawatt of this Dogger Bank project. And in very general terms, they say that one single rotation could power up UK household for more than 2 days. And so this is the size of the wind turbine. And then talking about the long distance connection of wind farms. So this is typically a offshore wind farm configuration. This is a simple configuration, but the detailed diagrams are we could go for very detailed. And here we have number of offshore wind turbines installed, radially connected, and the offshore wind farm locations and feeders. And typically it uses 33 kilovolts or 66 kilovolts AC connection to connect to the offshore substation. And in the offshore substation, it step ups to the transmission voltage. This could be HVAC or HVDC. Typically, the export voltage is decided by the voltage level at the point of connection. For UK, this is 400 kilovolts AC, and in the US market, it is about 230 and so on. And in AC connected offshore wind farms, sometimes it uses a midpoint reactive power compensation substation when the distance to the shore is very much larger or more than 100 kilometers offshore cable. Generally, for a cable, the break-even distance is between HVDC and HVAC about 60 to 70 kilometers. However, some project users, such as the first midpoint compensation project, is a Hornsea 1 project in the UK, which is 800 megawatt total capacity. Because people use the projects uses HVAC with midpoint compensation due to the technology maturity of AC technology and the know-how of the developers. And in the next slide, I will talk about both of these AC and DC technology a little bit in detail. And talking about the transmission technologies, as you can see here, in early stage of offshore wind farm development, HVAC technology has been used. And normally in these projects, at the grid connection point, a STATCOM or a synchronous condenser has been used to comply with the grid code requirement. In the first presentation, Dr. Brian broadly discussed about this compliance. I think in the next presentation also, Dr. Nilesh will talk about much in detail. And a set of static filters and variable shunt reactors are also deployed at the LV side of the onshore transformer to reduce harmonics and all the grid compliances. For example, in the UK, the metering point is at the LV side of the offshore substation. For Germany, it is at the HV side of the offshore substation, and in the US market, the metering boundary metering point is at the LV side of the onshore substations. For HVDC offshore wind farms project, normally they uses voltage source converter technology due to its flexibility in controlling active and reactive power independently compared to the thyristor control TCSC technology. And these are some of the general facts about these two technologies. And talking about some trends in the offshore wind farm development, recently there is a trend towards development of floating offshore wind farms because with the rapid development of offshore wind farms, most of the seabed closer to the shore has already been occupied. And also statistics show that closer to 80% of the world's offshore wind resource potential is available in the water depths deeper than 60 meters. And so if we wanted to meet with these net zero goals and all in the world, so going more away from the sea is essential. So the next generation of offshore wind turbines are designed to float out of the sea. You can see here there are like different type of foundation types. Basically, the present projects uses monopile and jacket or tripod foundations, but there are a number of projects. You can see that high wind, there's a demo project in Scotland, high wind, and there's a commercially operational one about 50 megawatt project up until running now. And you can see that the semi-submersible structures will be used in the future floating offshore projects. And also we can see that there is a trend towards that, like the cost per megawatt is forecasted to reduce over time, which is competitive to the bottom fixed wind turbines in 10 to 15 years of time. And just to summarize some of the generic challenges in the offshore wind development, which is also valid for any other renewable energy interconnection. The grid code compliance is a must, and for the grid operator from point of view, the grid codes are to ensure the security of supply and reliable power generation and the transmission. Therefore, now it's becoming a mandate to act all the grid connected renewables at least to mimic or act as classical synchronous machines with the battery storage and all. So there is a mandate with the grid code to comply with that. And also the V-grid connection, I think in the previous presentation, Dr. Tiwanka shows a nice plot about how the short circuit ratio is declining with the integration of renewable energy. And this is for a developer like Allstate, it's also a problem connecting large amount of offshore wind to the weaker grids. And the SIGRE technical brochure 671 on connection of wind farms to weaker HC networks defined the definition of weaker grids. So it's basically if the short circuit ratio is between 3 to 5, it's defined at weaker grid, or if it is less than 3, it's defined at very weak grid. So what happens when we connect the renewables to the weaker or very weak grids and need to identify what are the stability issues associated with connecting to the weaker grids, and there could be some unknown stability issues, and relay coordination studies and all sort of studies, pre-stage studies has to be done properly. Otherwise the system could got collapse in different events. And also one of the emerging topics discussed about is the subsynchronous interaction. What is this subsynchronous interaction? Previously, the subsynchronous interaction observed in wind plants have gained attention in the recent years. This is generally occurs between wind farm and series compensated transmission lines or the weaker AC grids. There could be two phenomena in subsynchronous interaction. One is the subsynchronous processional interaction with the mechanical unit and the power electronic devices, and the other one is the subsynchronous interaction between the series compensated lines or the weaker AC network with the more power electronic devices available in the wind farm. One example is 2019 London blackout. The postmortem studies found that one reason for tripping 800 megawatt Hornsea 1 wind farm, which is connected to the National Grid UK wind farm, there is an interaction between controller interactions between its onshore and offshore arrangements. So that is one of the reasons for tripping of this wind farm. So basically proper tuning of proper tuning and coordination of different power electronic devices is necessary to reduce these unknown and unforeseen issues in the future. And talking about some of the trends, so this is so people are talking about DC collection systems, whole DC connection of wind farms. Basically, this is my PhD work, and some talk about like whole black start capability from offshore wind farms. This is also a hot topic these days. Basically, the idea is to observe the capability of offshore wind farms to self-start without external sources and act as anchor generator to energize the mainland grid upon a total failure. So in the next few slides, I will talk about the offshore wind interconnectors, which is our main topic for today. Today, the offshore wind farms and interconnectors are separately connected to the networks, and they are operating alongside with each other. But the future would be like offshore wind and interconnectors work in harmony, and they could enable offshore wind and interconnectors work together as a combined asset. So this is one of the future trends working. They are all interconnected to one or couple of single hubs, and working as single assets is the way forward for future. Let's talk about some of the advantages of this concept in the next couple of slides. So the offshore wind interconnectors. So interconnectors already provide a way to share electricity between countries. That is not a new topic. In this image, it shows the point-to-point interconnectors between UK and the other neighboring countries. Offshore wind is one of the key enablers in the green transition to realize the targets promised during the COP26 Glasgow this year by various nations such as UK to become net zero by 2050, and also EU and some other countries as well. The multi-purpose interconnectors would allow clusters of offshore wind farms to connect in all in one go. So that is the purpose of an interconnector basically. So what are the key benefits of multi-purpose interconnectors? So mainly this to support the 2030 and 2050 climate targets pledged by different countries and different nations, and the other one is to reduce the impact of coastal communities with fewer individual connections and less constructions needed when we have multi-purpose interconnectors, and enable a reliable power flow of electricity that can turn up or down when needed. So this is one of the reasons to improve the flexibility of integrating renewables in the future, and generate a greater portion of electricity via offshore wind and harnessing more offshore wind available at the offshore sites, and provide significant cost reduction using shared assets and clusters connections. These are some of the key benefits of multi-purpose interconnectors. And in the next few slides, I'll cherry pick some of the two notable projects which are currently under discussion and the pre-planning stage. The first one is North Sea Wind Power Hub project, and the other one is National Grid and 1080 multiple interconnectors. So the National Grid is the UK TSO, and the 1080 actually it's Germany and Netherlands. They are operating in Germany and Netherlands as well. So this one, the 1080, what I'm talking about, is belongs to the Netherlands TSO. And talking about the North Sea Wind Power Hub project, so far energy policies in Europe have mostly been nationally focused, with international cooperation only recently starting up with these ambitious targets. And harnessing the power of the North Sea requires to look at the whole North Sea as a common area. And comprehensively, it requires rethinking how the energy systems of Northwest Europe can harmonize together. So this project is an ambitious new approach to the challenges faced by integrating renewable energy. This consortium was found in 2015 with 3 TSOs, Energinet Denmark, Gasunie Netherlands, and 1080 Germany for this one. And so there are a couple of configurations they are talking about. The first one is the radially connected wind farm with AC connection, which is typically currently, which I use point-to-point connection, and radial connected with HVDC. So there is a hybrid connection, and there are electrical connections. In the hybrid connection, it uses HVDC, and which connects to the multiple countries using a single platform. And the hub and spoke concept. So this is one of the new concepts that they are talking about to deploy in this project. The hub and spoke concept combines electricity transmission from wind farms to shore with interconnectors, and facilitate the integration of gas, electricity, and heating, those combined assets through the power to X conversion. So the hub and spoke concept is able to link the energy system North Sea in well-planned and coordinated network. So that is one of the objective of this project. And the other concept, hub and spoke with conversion, aims at producing hydrogen using, it's called green hydrogen, using offshore wind farms, and export to onshore via separate hydrogen pipelines. And the energy which requires to electrolyze the hydrogen will be used from the energy generated from offshore wind sites. And we can identify few characteristics of this hub and spoke concept. It's transnational. What do you mean by transnational? It connects multiple countries through the hub and spoke concept, and it's hybrid. Combined interconnections with offshore wind farms, and it's cross-sector, so it's able to integrate different energy access and energy carriers. So according to their plan, the first hub project aims at realizing by 2030. However, it still needs to address the concerns regarding mainly the policy topics and interdependencies with different markets and all. So we hope that this will come into reality in the future. And the other project is the National Grid and 1080 multipurpose interconnector. Unlike the previous multinational North Sea wind power plant hub project, the aim of this project is to harness the full potential of offshore wind to meet the decarbonizing targets of the UK and Netherlands. So this interconnection is already available, but it's not an actual project, but it's a reclassification of existing interconnector to facilitate multiple services which is required by both the countries. And finally, I'd like to highlight some of the discussions going on about the Danish energy island. So they call it, it's a Mars mission for the energy system. They expected to develop 10 gigawatt capacity of offshore wind power at energy through the energy islands will form a backbone of power generation. And one of the notable feature is that it's going to be solely on inverter based or power electronic based device infrastructure will be used to integrate the battery energy systems, solar PV, offshore wind in these islands. And this removes the concept of inertia and hence takes away the energy buffer available in our traditional power systems. And this will be, for that, it needs to develop a lot of advanced software modules and complexity, address the complexity of integrating multiple resources together. So this is still under discussion, and think they are going to put the tender on like in next couple of years for the development. And to summarize, talk about this, we talk about the future decarbonization of power system, and it requires a large amount of flexibility, and the hub and spoke concept could offer a solution to the challenges in the integration of renewable energy in the context, at least for in the Europe, and the green fuels like hydrogen can play a vital role in cost-effectively integrating large volumes of offshore wind energy, and it requires to conduct multiple in-depth studies to gain future knowledge on system integrating, on how the energy landing zones, how to use effectively and cost economically, and energy conversion and supply chains, and also innovation and technology readiness level of these new concepts. And finally, to develop evidence-based discussions and to tackle these technical economical studies is very much important when we introduce new technologies and new concepts before it goes to the real demonstration projects. This is my presentation, and thank you very much for your time.
Thank you very much, sir, for the very informative presentation. And the last presentation will be done by Dr. Nilesh Modi. Dr. Nilesh Modi is an manager of operational analysis and engineering team at AEMO. He has been worked with AEMO since 2012. Nilesh has been involved in various key projects documents published by AEMO. For example, the review of the South Australian System Black Event and System Strength Assessments for South Australia. Currently, his focus area is power system operation with high penetration of inverter-based resources. This is over to you, sir. Thank you.
Thank you, Sumudu. I hope you can hear me okay, and my slides are coming up.
Yes, sir.
Yes,
We can.
yes.
That's good. Thanks. Right. Good afternoon, everyone, and thank you to National Science Foundation and IEEE Power Energy Society of Sri Lanka for providing this opportunity to share Australian experience of managing a grid with a high share of renewables. So you have heard about details of generator connection, components, and its importance of incorporation of PV and batteries into the grid, and the details about offshore wind farm connection. Now, during this presentation, I'm going to talk about AEMO experience of managing a grid with high share of renewables and energy storage. So in comparison to previous talks, this is going to be more like a 30,000 feet view of a system operation. In first few slides, we will touch on operational challenges associated with high share of renewables. And then we will take a deep dive into how transmission connected batteries can help addressing some of those challenges. For the purpose of this presentation, I have used South Australia as an example region, but the concept presented here can be considered for other power systems that are facing similar challenges. So the first one, it's important to notice the views expressed in this presentation are those of the presenter and do not represent those of AEMO. And the information in this presentation does not constitute technical, legal, or business advice. Before relying on it, you should make your own inquiries. AEMO and the presenter do not guarantee the currency accuracy or completeness of the information in this presentation and are not liable for any statements or representation in this presentation or any omission from it or for any use or reliance on the information in it. With that aside, let's start. Okay. So I'm using this slide and the next slides to set the scene. So we all know that many power systems around the world are going through a transition, and it is occurring at much higher rate than expected. If we take an example, in 80s and 19, it would take approximately 6 odd years to build 200 megawatt of power plant. And fast forward to 2021, it can be done under a year. Okay, we have seen that in Australia. Building a plant is just one aspect and probably more like a key index for general public, utilities, participants, or owners. Another equally important aspect is to integrate the plant into broader power system markets, developing necessary technical envelope to operate the system. So it's not all about connecting the plant only, it's also about integrating it to wider power system as well. Well, even if one plant is being built in a year, that's still okay. It does not put a lot of pressure on analysis that needs to be done to assess the impact of it on overall power system. But in 2020, I apologize, the data is 1 year old. I'm still waiting for 2021 data. We in Australia, NEM Power System, added 12 new plants with total capacity of 1.5 gigawatt and another 32 projects of 3.3 gigawatt capacity were in pipeline. And to make it more complex, the new generators that are being integrated into the grid are asynchronous, relatively new, and comes with several unknown compared to synchronous generators, where we as an industry have several decades of experience. So the previous slide was about growth in generation. On the other side, we are seeing reduction in operational demand. And to be specific, I mean the demand to be supplied from transmission connected generators. This reduction in operational demand is driven by large uptake of distributed energy resources, such as rooftop PV system. In Australia, we are seeing reduction in operational demand, and the NEM, which is Australian East Coast Power System, has seen its minimum demand, a record minimum demand of 12.9 gigawatt in October this year. We have seen a traditional generation fleet, that is a thermal generations, spending more time closer to their minimum stable operating levels. And this is largely driven by combination of low operational demand and high generation from renewable energy resources. The forecast is suggesting that demand is continuing to sink or shrink, and we are going to be in low operational demand period for extended period of time. And it is likely to occur in the middle of the day. The figure on the left is our forecast coming from one of the publication. And the figure on the right, which is just popping up now, is the South Australian demand and a generation mix for a day when we had a record minimum operational demand of 104 megawatt. This is typically 1.2 gigawatt system. And on the middle of the day, there was a need to only supply 100 megawatt. And as you can see, the native demand is still high, is in the range of 1.2 gigawatt, but it's being supplied by rooftop PV generation, shown by yellow area. In spite of all the changes that I mentioned in the previous slides, need for power system operation do not fundamentally change. Some of them are shown in the slide, not all. We still need sufficient voltage and frequency control. We need inertia to reduce rate of change of frequency following a disturbance. sufficient system strength for acceptable performance of inverter-based resources, sufficient amount of reserve to manage unforeseen events, and if things go wrong, we need restoration services to restart the system. And all of this when we are transitioning to low carbon energy future. We are noticing change in generation fleet at the time the grid is dominated by synchronous generation, while there are times when the grid is dominated by asynchronous generation. Inertia of the grid would change depending on the generation online and can often be very low. There are few changes or few challenges associated with managing system strength and low demand period, which necessarily needs sufficient voltage control. The analysis of the system often needs to adopt appropriate tool to assess the system security. It could be RMS tool, or it could be an EMT tool, depending on how you are operating your grid. The system continuously moving between large scale generation and distributed energy resources. During daytime, when your native demand is largely supplied by rooftop PV, there is not a lot of need for large scale generation. But at night, there could be a need for those large scale grid connected generators. We need to start exploring new ways to restart the system, such as including wind and solar generation to support system restart or restoration. Use of grid forming technologies to support this process as well. So there are so many challenges. However, for this presentation, I have picked up system strength, and we will take a little deep dive into system strength. So system strength as a concept, it is an inherent characteristic of grid, and it's related to the proximity to and amount of synchronous machine online. On the right side of this slide, you can see a diagram that conceptually try and explain system strength. When a system has very low amount of IBR, and the location of IBR is inverter-based resources, and when the location of IBR is relatively close to the synchronous machine, it's called high system strength scenario, and is shown by number 1 in the figure. Now, even with low amount of IBR, if their location is far from synchronous machines, it can be categorized as low system strength scenario, which would more prone to instabilities. And this is shown by number 2 in the figure. Even if you have large number of synchronous machines in the system, but as you increase the penetration of IBR, the system strength reduces. And this is shown by number 3 in the figure. It's important to note that the system strength requirement depends on the amount of IBR. Sometimes it's a megawatt, and sometimes it could be MVA, that is the number of wind turbines or number of inverter you connect to the grid. So what are the issues? Okay. In a day-to-day operation, like a system normal, a low system strength can result into multiple undesired system performances, such as a poor voltage regulation, potentially leading excessive voltages, violating steady state limits. Brian mentioned a simple example of that, which was observed during connection process. When a reactive power plant is switched in, it can result into a larger than expected voltage change. And this could result into undesired or sometimes unstable interaction between fast control systems that are within the close proximity to each other. It may happen that a small change in the power flow condition could lead to a localized voltage collapse in that area when the system strength is low. Following a disturbance, a much wider propagation of voltage dip can be seen by the system, and this could result into large amount of IBR seeing the fault and go through their fault right through mode, where they will momentarily reduce their active power generation. And this could be a problem, particularly for a smaller grid with large amount of IBR, such as South Australia or Tasmania, where momentarily you will have energy deficit. During the fault, as the voltage angle movement is large and fast, often it could be difficult for PLL to keep a track of the angle change, and you might see instability arising from the plant, and plant can trip off. The voltage angle transient could be misinterpreted by protection system, particularly rock-off and the vector shift protection. They are prone to have a mal-operation during a low system strength environment. So what are mitigation measures? There are a number of them, and I'll quickly go through one by one on this slide. The first one is the temporary constraint. Okay, we have exercised this in Australia. We have managed to get around the low system strength issue by reducing the number of inverters online from grid connected solar farms. To give you an example, this is how it's going to look like. The blue trace is the post disturbance voltage changes as seen in a simulation, which was also further verified by system test. When I say system test, is a real-time test. So when you have all the inverter at 100% dispatch, you see this voltage oscillation popping up following a disturbance or a contingency. And when you reduce the number of inverter, the magnitude of this oscillation substantially reduces. So this was a temporary constraint which was put in place until we explore alternative solution. Another solution is installation of synchronous condenser, which has been exercised by South Australian transmission network service provider, which I will provide a little bit more detail in the next slide. So this is, again, if you do not have any synchronous condenser, you could see post-fault voltage oscillation or post-disturbance oscillation appearing in the system, and synchronous condenser can help to stabilize the oscillation by adding system strength to the network. The other option which we have implemented in West Mori area is a tuning inverter control. So the option is to tune the inverter control such that they are specifically configured to operate as expected during extreme low system strength conditions. And the third graph on the right shows that what you can achieve, which is quite similar to what you could achieve with synchronous condenser. Okay, so the solution is to go and tune the control system parameter, which is very involved exercise. The other option is to use the grid forming inverters. And the figure on the top right shows that, okay, well, if you have grid forming inverter, that can also provide you a system strength, and it can help to stabilize the voltage oscillation which you would see following a disturbance. So not only one, there are quite a few options available to address system strength issue. Okay, something is popping up here. Should be okay. So let's go into the synchronous condenser environment. So South Australia has one of the highest penetration of IBR, not only in the name, but worldwide when comparing to the similar size system. It has seen 150% instantaneous penetration of IBR at times. Okay, so that degeneration from inverter-based resources, or you can call it renewable energy sources, is 50% more than what is needed by the localized network. And so far, to maintain sufficient system strength, AEMO was relying on synchronous generators within South Australia and directing them to keep online. In 2018, we declared a system strength shortfall in South Australia, which resulted in transmission network service provider, TNSP, to go and procure system strength services, and they decided to install 4 synchronous condensers in South Australia. 2 at Devonport, which is shown on the figure, the top part of the middle of the figure, and 2 at Robertstown. So there are 4 synchronous condensers which are now in commercial operation, in South Australia, which has resulted in filling the system strength shortfall, which was declared in 2018. Now, these synchrons are a little bit different than traditional synchrone. You'll get it. These are high inertia synchrone. It has a flywheel, and each synchronous condenser have 1100 megawatt second of inertia, which is provided by flywheel. Okay, so let's go and look at a bit more about the battery energy storage system. So I'm using this slide to set the scene again, to give you an idea about what we see in our part of the world in terms of transmission connected batteries. The first large scale BESS, battery energy system, was connected in the Australian power system was back in 2017 after South Australian blackout in 2016. At the time, it was 100 megawatt, 128 megawatt hour battery. And at the time of connection, understand this was the largest transmission connected lithium ion battery, popularly known as a Tesla battery. Those of you read news, it's often mentioned it's a Tesla battery, Tesla's big battery in South Australia, but it is registered as a Hornsdale Power Reserve. And recently it has already expanded to 150 megawatt, 194 megawatt hour capacity. Currently, as we speak, we have 260 megawatt of transmission connected batteries operation in South Australia. Well, I should say it has increased by 300 now, because in earlier this week, the 300 megawatt of battery, often known as Victorian Big Battery, went into a commercial operation. Okay. So in near future, we are expecting a few more batteries, and collectively it will result into about 600 megawatt of battery energy storage in the name. And when we look at the emerging or publicly announced battery, we're expecting about 18 gigawatt of batteries coming into near future. And these are those who are not formally submitted application to connect, but they are going through their usual process of development approval, acquiring land and finance, etc., etc. And even if half of it goes ahead, it would be like a couple of large power stations. So in terms of power system security application, with that background in mind, what I will discuss is some of the, or let's say few system security applications. The frequency control, okay. When we look at the response from the battery, again, I'm talking about the transmission connected battery, so keep your system operator hat on, to a slow change in the frequency and the fast change in the frequency. So when battery responds to a reasonable large change in the frequency, how much time it will take, how responses look like, that is what we will have a look. Another application we will touch on is the SIPS, or they call it System Integration Protection Scheme, often known as a special protection scheme. Sometimes it is known as a remedial action scheme. This is where we look at how batteries can be incorporated to improve system resilience. And I'll take again South Australia as an example. The next one is the virtual power plant, which I'm not going to cover in this presentation, but I will give you some references to look at it. So all the references are publicly available. You can go and look at it, the virtual power plant detail. And the last one would be some of the emerging applications of batteries, such as inertia substitution or grid forming batteries and the application of grid forming batteries. So let's look at the first one, the frequency control. Okay, I've divided that in two parts, the regulation and the contingency. So this slide shows how a battery, which is particularly in a regulation services, that is to correct the small changes in the frequency through automatic generation control system through AGC, would respond. The figure on the left is a comparison between the command set by our AGC system and the response from battery. The figure on the right is response from a large conventional steam turbine. And the duration of this figure is 1 hour in both figures. So it's clear how battery closely follows AGC target as compared to a conventional steam turbine. There are a number of other things that needs to be considered during this comparison, such as large steam turbine have complex dynamic systems, time constant associated with thermodynamics, and other slow responding system. On the other hand, those time lags associated with thermodynamics, etc., are largely absent in batteries. When we look at the response after a contingency or after a disturbance or less large disturbance, on this slide, there are two examples on how batteries responded during a real life event. One on the left is an event that occurred in 2018. The event was an under frequency event for about 10 seconds and followed by an over frequency event. And you can see in the figure on the left how quickly battery changed the direction from generation to load. Okay, so you can see it's relatively fast in absorbing the megawatt when the direction of the frequency changes. And the figure on the right is the response from all three batteries of South Australia to an over frequency event occurred in 2019. And what we can observe here, the change in the frequency was about 0.9 hertz. The frequency is the blue one. And the change in the megawatt is about 120 megawatt. So when you do up a high level calculation, it would come out to be 1.7% droop on 150 megawatt of installed capacity. And it is largely matches with how it was configured to operate. Just one more slide on the fast frequency control. And this is another way to show how batteries responded during the same event. I'm attempting to show fast frequency response capability of batteries here by reversing the secondary y-axis. So just pay attention, right? The blue trace is for frequency on the left side of the figure. So when you see blue trace is going up, in fact, the frequency is going down. Have a look at the secondary y-axis, how it is reversed on both slides. So a key message here is how megawatt response from battery is following frequency very closely. There is a delay, but it's very small. A sub-second response is well within the capability of batteries. And also it would depend where the frequency is being measured. What our experience says that some large-scale battery measure frequency at power park control level and then send a signal to inverter. So inverter would change its output to respond to frequency change. While some measure the frequency at inverter level itself. So those responses could be faster because that means there is no delay between PPC and inverter. Going to the next application, these SIPs or RES or SPS, another application of battery. It is integrated in what we call System Integrity Protection Scheme. A little bit of background on this scheme. The intent is to detect unstable power swing between South Australia and rest of the NEM system. The figure on the right is how the South Australian power system looks like. Following a detection, it takes action if it detects the loss of synchronism between South Australia and the rest of the NEM regions. It has three stages. The stage one is where it makes use of batteries. Stage two is a preemptive disconnection of load to defer separation of South Australia. And the stage three is actually opening up the border and forming an island. And for the benefit of audience, the figure which is on the right side of this slide is the South Australian power system connected to other regions of the NEM via one AC interconnector and one DC interconnector. And the distance between the AC interconnector that is monitored through the scheme and the battery is approximately 800 kilometers. So how the scheme would work? The scheme would detect the potential loss of synchronism between South Australia and Victoria or other NEM regions. If it detects the potential loss of synchronism, it will send a signal to battery, and the battery has reserved megawatt. So battery would discharge its megawatt into the grid and thereby try to relieve the load on the interconnector and potentially defer the loss of synchronism between South Australia and other regions. The next application is about the inertia substitution. So we as AMO use the battery for inertia substitution, particularly for South Australia, where we have developed interrelationship, or let's call it relationship, between FFR, the fast frequency response, and inertia requirement, as shown on the right side of the figure. Indirectly, we are substituting some portion of inertia or some part of inertia with FFR and still meeting the system security requirement. So as an example, if we can pick up any dots on the red line on the figure on the right side, if we have 120 megawatt of FFR available in the grid, then the inertia required to meet the system security is about 11,000 megawatt second. On the other hand, if we have 200 megawatt of FFR available, that inertia requirement will reduce from 11,000 to 6,200 megawatt second of inertia, and it will still achieve similar outcome. Okay, so that shows that okay, you can substitute some portion of your inertia by procuring fast frequency response from battery, and that is particularly used for South Australian system. Figure on the left is trying to show the relationship between inertia reduction, how much inertia you can reduce as in percentage, and the FFR. And the key message here from the figure from the left is, with other things being equal, the higher inertia substitution can be achieved for low inertia system with increase in FFR. So in a nutshell, the importance of FFR is more noticeable when you have a low inertia grid and your size of the contingency is relatively high. The next application is the grid forming, which previous presenter has briefly touched on. And some of you, if you don't know, we have our first transmission connected grid forming battery in Australia. We call it Dalrymple BESS, the Dalrymple Battery Energy System. It is in the remote part of South Australian network, which has a wind farm very close to it, and it is also supplying a local load. It has demonstrated a smooth transition between a grid connected to island operation. Because it is a remote part of the network fed by a single radial line, if the line opens up, the battery would form an island with wind farm and the local load. And the wind farm capacity is quite large than the local. So the wind farm would disconnect or reduce its output generation to meet the local load. So figure on the top right shows that smooth transition. So the red line is where the transition has occurred. And you can see that during the fault, it has provided a bit of a high current, and then it has stabilized and supported the local load. The second application which we have, by the way, Dalrymple is in South Australia. Dalrymple BESS is in South Australia. The second one is HPR or a Tesla battery, if you like, again in South Australia, which was trialing 2 inverters in what they call it virtual machine mode with various inertia constant. Inertia constant they picked up was 5 and 50 as a trial. Now, while the trial was occurring, there was a reasonably large frequency disturbance occurring in the grid. So of course, those 2 inverters were in a virtual machine mode, so it would definitely respond. And the response is on the right side of the figure on the bottom side. You can see the response by the orange and in the other purple line. What you can see is the response is largely driven by rate of change of frequency. So if you calculate the rate of change of frequency of the frequency trace, you will get higher response when the rate of change of frequency is high, and you get a lower change when the rate of change of frequency is low. This information is also available, and I have provided the link to the publicly available website. So if you are interested in looking into more detail, whether it's about Dalrymple battery or HPR or Onstel power reserve battery, that is available online. So that's probably summarizes my presentation. So in summary, what we looked at, I particularly focused on the application of battery. So we discussed about frequency control, how battery can help in regulation and the contingency. We discussed one application of the battery for special protection scheme. We briefly touch on how it can substitute inertia in those two slides, and an application on the grid forming. Other applications like reliability energy, they are very well known, and people have been using it for energy purpose, energy arbitrage, and the reliability application in the remote part of the network as well. One of our NSP, network service providers, to say, has a portable batteries on the containers. So when they are taking an outage of very remote part of the network, they know that they can't meet the supply. So they go and go take that container, drive that container down to that location, and hook up the battery to the substation to provide sufficient energy and maintain their reliability standard. We also briefly discussed about the South Australian power system and the operation of the power system, and focused on the system strength. If you are interested, provided the link. I believe the presentation would be shared with attendees a bit later on. You can go and refer to this this material if you are interested. I think that's pretty much it, what I had to cover. Thanks for listening, and happy to answer a few questions.
Thank you very much for the very informative presentation, Dr. Nilesh Modi. Now is the time for the Q&A session. If you want to ask questions, please use raise hand option. This session is moderated by Professor J.B. Ekanayak. He is the senior professor at the Faculty of Engineering, University of Peradeniya, and also he is a member of the Steering Committee on Cost-Efficient Energy Resources and Energy Storage of National Science Foundation, Sri Lanka. This is over to you, sir.
Oh, thank you very much, Samadhu. I think we had very interesting and informative presentations. And also kind of coverage of the regulator, the industry coverage, as well as consultant. And I'm sure most of the questions people were asking kind of has been touched upon by these the presenters. These questions people frequently ask from us, so those questions are, I found answers to most of the questions. While we wait people to kind of gather questions, let me put forward the two questions I found on the chat box. This was from Namish Mustafa, one of our energy experts in the country. Is asking, if possible, please share successful business models of behind-the-meter battery energy storage systems where aggregators, particularly integrating solar PVs. I think it's probably for Brian and Nilesh. I know that this is
I can take a crack on this, Brian, if that's okay, and you can top it off.
Yeah, please,
Yeah, sure, no problem, Nilesh. Thanks.
Okay. Look, we are system operators, so we largely stay away from those business case behind the battery energy storage system and how it can actually average out the cost of their supply. What I understand that there are aggregators who goes and the place a contract with the individual batteries and use those batteries to bid into the market, electricity market, which has a cost associated with it. We had a trial of virtual power plant where we integrated number of household batteries into through an aggregator, and then that aggregator was dispatching that battery into energy market in a real time, similar to like a wind or solar farm would submit its bid. And that could be one of the proposition to consider when we look at the business model for those batteries at this stage. There is no, at least I'm not aware of, unless Brian, you know that in South Australia there was a discussion about providing a grant to install a home energy storage system, but I'm not fully across that development.
Yeah, I think virtual power plant project may be a good one. There are some public publications available online, but as Nilesh said, I don't really think we can help with getting to those business cases. Sometimes those are considered as secrets, their own IP. Unfortunately, those might not be available, but certainly you might be able to get something out if you refer to that virtual power plant trial. In addition, I would like to mention one project in South Australia that was done by SA Water. They had an intention to achieve zero cost for their pumping stations. So they upgraded their old pump, most of the big pumping station by adding batteries and solar farm. It is not really 100% behind the meter, but the intention is to make zero import at the connection point. Some publications are available, may not be the business case and financial model, but at least you can get a better understanding. Following the presentation, if I can find links, I'll probably share with the organizers, then they can pass that on to the group with the presentations later on.
Okay, thank you very much, Brian. Namish, do you have any, I can see that Namish is online, any kind of extended questions to that, or you are happy with the answers?
In fact, technically the solution is clear, but in fact, we are investigating the potential of aggregators, because at the moment Sri Lanka does not have aggregators, but at the same time the rooftop solar has really grown up quite fast. So that's what I was wondering, whether there could be any models where those can be implemented in Sri Lanka in time to come. The technical aspects, of course, are clear.
Yeah, look, I probably provide a little bit more information on the solar system, and this is probably might help or may not. But the similar to one of the slides previous presenter presented, the grant provided to household to install solar, right? So we had that, at least in Queensland, a 44-cent grant provided per kilowatt hour to install rooftop PV. That was by government. And when you look at the electricity charges, it was about 20 cents per kilowatt hour. So it's no brainer, right? So when you get paid 44 cents for 1 kilowatt hour, and electricity price is 20 each kilowatt hour, so that would easily even out in a very short time. So that could be one of the example of a business case, but that was not by aggregator. That was the support provided by the government.
If I add on the UK side, the aggregators are actually there are like products in the national grid which could be able to provide the fast frequency support and all from all these ancillary services. So I think in the national grid website for the aggregators are available to support the different ancillary services required by the national grid. I think there are like from aggregators like small aggregators which requires like batteries and solar energy and all. There are different options available in the UK market in terms of aggregator.
Okay, thank you very much, Kayan and Nilesh, for adding. So let me move on to the next question, which was on the chat box. I think it's probably for Tivanka. In local grid, we have voltage THD even up to 8 to 10%. Is it required to maintain injecting current THD to be below 3% as per IEEE 1547 when the voltage THD is high? Maybe Tivanka or Brian can add some. You want me to repeat the question?
I'll probably touch on briefly on that one. I believe he's asking about grid code compliance, in this case, 10 THD, whereas the grid code says 3 THD. Was that the question?
Yeah. Basically, you know, typically you have 8 to 10%, but the grid, not the grid code, IEEE 1547 demand for 3%. So.
Yeah, I think
because actually these I asked that question because these voltage THD is about like 8 to 10% because we can't control the voltage THD because it's from the supply. So because our supply is not very good, so that's why because it has 8 to 10%, sometimes high as 8 to 10%. So but we inject the current, so we have to control the current THD. So according to this IEEE standard, like it has to be below 3%. So is there sort of requirement when the voltage THD is high? I mean, can we inject a higher THD, allowed higher THD on current as well? Or like, I mean, it still has to be even lower than 3% still?
I probably think that's tied up with the grid code applicable for a particular region. So let's say power quality can mean different things depending on the operator. Whereas in one grid, higher THD may be acceptable, whereas in the other grid it may not be acceptable. So I would think you might have to read that question to considering what is required as per the power grid. This may not be possible in Sri Lanka, as understood. There's no solid established grid code for that. But typically,
because it says like we have to adhere to this 1547, which is our current injection should be less than 3%. But the issue is voltage THD sometimes go to 8 to 10%. So when the voltage THD is low, like our controllers will actually support it. But when the voltage THD is going even 10, like then current THD obviously will.
I think I can probably. I mean, we have like the CEB is using IEEE 1547, but our distribution grid code is under review right now. What we are using is the very old distribution review. So it's a kind of a, we are in a what you call a transient scenario. So I think this is a question we may need to put forward to the guys who are drafting the distribution grid code right now. There's a committee working on it. So let's keep that aside and move on to the question raised by Professor Kitsildian. What are the key?
Janaka,
yeah,
sorry about. I got disconnected for a couple of minutes. So if there was a question, so I would be happy to answer.
It was this PhD question. Then I realized that it's not for you; it's more for Brian's territory. So that's why I go. So thank you.
Glad it got okay.
So the next question is from Professor Kitsildian. What are the key challenges associated with using VPP in frequency control? Nilesh, you want to come in or?
Yeah, I can take that one. What are the challenges? Okay, I think the large challenge would sit in the communication domain. Because VPP, they are distributed all across geographical areas. So you need to have a proper communication between what the batteries are doing and what the market needs, right? So you as an aggregator would have those kind of facility available to you. in terms of technical challenges, it's hard to see that there would be any difficult technical challenges you would encounter when you want to use VPP for the frequency control. The only challenge would be how do you aggregate that? How do you make sure that what you have committed to market is what you are providing following an event? So those kind of checks and balances, which someone need to do it after an event occurs, that would be a critical part of it. And we have those challenges now as well. So we are working with the VPP provider to improve the resolution of the measurements so that we can actually look how VPP is responding. But if you go to that one of the reference on my slide regarding VPP, it has a report available which actually would show you how VPP responded to a frequency event. If that answers that question,
Okay.
I hope.
Okay, thanks. Kitsiri, any?
Yeah, that's fine. That's fine.
Okay,
So it's mostly
thanks.
in the ICT domain. That's what he says.
Okay, thank you very much. So I will maybe to conclude, because we are now reaching the more or less the end of the session. So let me ask a simple question from Brian or Nilesh. Do you have a full EMC type model of the Australian system, or you have only components in EMC kind of platforms?
Nilesh, would you like to take it?
Yeah. I can take that one. That's fine. So I believe you are talking about electromagnetic transient model.
Yeah. Sorry, EMTP
okay.
time. EMT type.
Okay. Right. Okay. Yes. So we have the full scale EMT model of the entire power grid. So that includes all 5 regions of the name, all the way going up to 66 to 11 kV. Currently, we are working on developing the detailed EMT model for the load, which could include how distributed PV can be modeled in a distribution grid. But as far as the transmission grid is concerned, we have a full scale model of the EMT system, which is what our connection team, Brian and his colleague, are using for generator connection. So if the connection application comes in, they use we call it wide area model, or there are a number of names floating around. We call it full state model or wide area model, but it captures probably, I don't know, maybe about 250 IVR, and then around 70 to 80 synchronous generator, and probably 4,000, 5,000 buses. So it's a very complex model which we have developed in-house.
Thank you. I think it's Shavi. Shavi, is your question short? I can let you.
I have not yet floated my question. I just wanted to capture something and just ask a response. We have about, I think most of you know, about 5,800 megawatts installed, and about 2,000 is firm thermal, and about 2,800 some kind of renewables, including large scale hydro storage plus variable storage, variable renewables. So in this scenario, I'm just toying with the idea. Before going for BSE, what's the big problem in analyzing and finding out, trying to convert some of the storage hydro to not really pump storage. Pump storage is also on the cards, so it's not been actively pursued so much as it should be, to overcome this short-term, long-term, steady state, all kinds of issues with regard to load variations, which is very typical to Sri Lanka, which is highly time dependent. And so before going for thinking of large-scale BSE, which is going to be staying with us as hardware after their lifetime, useful lifetime, this is going to be another issue. Why don't we, I should be a culprit myself for not having done so, I did a little bit of research on the active storage utilization to store these variabilities of the renewables, which is very real, extremely real right now. What is your experience in Australia? And can perhaps Janaka and others who are still in service active very much. Take on this issue before you get on to expensive BSc, because where is this is because one of the last public events that I attended in 2014, which was entirely on a summit on battery storage. I raised this issue with at the time in Sri Lanka, which was not so highly renewable dependent. As a renewable, it's variable renewable dependent. And they, in fact, all of them who were there at the summit said, why not you first think of utilizing or managing your own hydro storages before going for BSc, which is for countries that you don't have any storage in the system. So your thoughts on both the international panel as well as Janaka's is very much interested, very much welcome. And I really encourage people like Janaka to get on with this proposition before we jump onto this BSc, which has its own issues, given excellent presentations you made on how best you have overcome some of the problems. Thank you.
Thank you very much, Shavi, for that thoughts. I think, I fully agree with you. We are having that advantage compared to many countries. I don't think that many countries has that luxury, but countries are making such a luxury based on the hydrogen storage. People are working on hydrogen in many regions, and I'm sure if you start this debate, this will go on forever. Everybody is, like we are reaching more or less, past the end of the session, as well as some of our resource persons need to move away to some other meeting. So let me conclude this session, thanking the 4 resource persons, Dr. Brian Perra from AMO, Dr. Tiwanka Vijayakon from Huawei, Dr. Gayan Abenayaka from Austin Power, and Dr. Nilesh Modi again from AMO for their very informative and thoughtful presentations, which are, I think, very useful for our audience. We had fair amount of audience before we kind of started the Q&A session, and it's dropping. So I think it's time for us to conclude this session. So thank you very much again, and good evening to the Sri Lankan audience, and good morning or good night to the Australian and European resource persons. Thank you very much.
Thank you very much.
Thank you very much.
Thank you.
Thank you very much, sir.
Okay.
Thank you very much.